Okay, testing. 1, 2, 3, 4. Testing. Okay. Okay, let's go ahead and begin. Okay, today we're going to do chapter 16, exam review. I would encourage you to download this or bring this up on your desktop so you have the questions to reference. I'm going to do the same. Just so that I don't have to keep scrolling back and forth. Okay, so first one is find the gradient of the vector field f of x f of x xy f of x y z is equal to x cosine 3y over 7z. Okay. Okay, let's see what we got here. Okay. Let's go back. Okay, x cosine 3y over 7z. Okay. Okay, so we want f sub x, f sub y, whoops, f sub y, and f sub z. So we can get the gradient vector. F sub y and f sub z, right? So this is number 1. Okay. So f sub x, that we're just going to treat the cosine 3y 7z as a constant. And when we take the derivative with respect to x, the x goes away. And we're just left with the cosine 3y over 7z. Okay, so that'll be my x component. Okay, f sub y. Okay, the x is a constant, so that just stays in front. Cosine becomes negative sine, so x times negative sine 3y over 7z. So this 3 over 7z gets treated like a constant. So 3 over 7z. So using the chain rule, I do a negative sign for the cosine, and then the 3 over 7z goes on the outside. The y is, the derivative of 3y over 7z when y is the variable and 3 over 7z is the constant, just becomes the constant 3 over 7z. And so then I can simplify this or combine some things. This is going to be negative 3x over 7z sine of 3y over 7z. Okay, so that's f sub y. Okay, f sub z. Okay, this one, I'm going to rewrite this function as x cosine of 3y times 7z to the negative first power. That's just going to help me to differentiate. So I'm going to get my x. This is going to be, again, negative sine of what's in, that's just going to be negative sine of the inside. I can just rewrite that as 3. I can keep it as the 3y over 7z. Okay, and then let's take the derivative of the inside with respect to z. Well, that's going to give me, okay, a, I could actually pull that 7 out in front and make it 3y over 7. And then z to the negative 1. How would I differentiate z to the negative 1? That's going to be negative 1 over z squared. Okay, and so I'm going to simplify all of that. The negatives cancel out. Negative, negative is positive. And I get 3xy over 7z squared sine 3y over 7z. Okay, and so when I take the gradient of this, the gradient of f, okay, that's going to be these partial derivatives and their components, ijk. Okay, and I'm not just kidding about that. Okay, so this is going to be cosine 3y over 7zi plus, or actually it's going to be a minus 3x over 7z sine 3 y over 7zj plus 3xy over 7z squared sine 3y over 7zk. And that's my gradient. Okay. Okay. If you have any questions on anything, please let me know. Okay. Okay, number 2. Let's see what number 2 is here. It says find the work done by the force field 30x plus 15 times 2y plus 1. Okay, so 30xi plus 15 times 2y plus 1. So let me write that down. 30xi plus 15 times 2y plus 1. I think that was a j, right? Yeah, 15 times 2y plus 1j. Okay, subject. So that's the force field. Okay, subject to this path r of t. This is kind of be the line there that we're going to be following. Okay, the trajectory r of t. Okay, and so that's going to be t minus, can I get rid of that? X. Thank you for the notification. Okay, that's cool. Okay, r of t is equal to t minus sine t I, right? And 1 minus cosine tj. Okay, so we want to find the work done, which is the line integral f dot dr. Okay, now keep in mind that you want to know if this is a dr or a ds. Okay, dr is for work, and that's going to be a different evaluation than if I have ds. Okay, ds is for a line integral in which we're using the arc length formula. Okay, dr we've already parametrized things, and so we don't use the arc length formula for that. Okay, we don't do the square roots. But if you have a small ds, small s, okay, I know it's a kind of a notation pain, but if you have a small s, then that's your arc length formula, right? So that's your 1 plus d. If you're parametrizing this would be, well, it's just your arc length formula. So 1 plus d dx. Okay, so this ends up being in terms of x, y's, and z's. Okay, for your small x. So this is dy dt squared. Okay, plus dx dt squared. Okay, so you use that if it's a small s. Now, keep in mind there is a difference between the little s and the big S. The big S is a surface integral. Okay, so I know it gets a little confusing between the small s and the big S, but just keep that in mind. Okay, but in this case, we're using dot drs. Okay, so we're just going to parameterize and then take the integral. This is going to be equal to, okay, the integral, okay, over that curve of f of r of t, okay, r prime of t dt. Okay, and those are dotted. Okay, so I need to know, well, what's r prime of t in this case? Okay, so r prime of t is equal to, okay, 1 minus cosine t, okay, I, plus sine tj. Okay. Okay. So now we're going to put it together. Okay. F is 30x. Okay. And what is x? X is this guy here. And what is y? Y is this guy there. Okay. So we're going to put this together. Okay. And what is t going from? Okay, well, t, they tell me in the problem, t goes from 0 to 2 pi. So let's do that, 0 to 2 pi. Okay, so let's set up the integral 0 to 2 pi. F of r of t, that's going to be 30 times x, which is t minus sine t. Okay, j, okay, plus 15 times 2 times y, which is 1 minus cosine t. That's a minus sign. 1 minus cosine t plus 1 I. Okay, or sorry, I don't know why I'm messing that up. This should be an I, and that should be a j. Okay, and then I'm going to dot this thing with r prime of t. So dotted with, I'm not going to write the whole thing. I'm just going to go r prime of t here, dt. Okay, because I'm going to dot this thing with the thing above it. Okay, so I'm going to dot product this. So 0 to 2 pi of 30 times t minus sine t times 1 minus cosine t plus 15 times 2 times 1 minus cosine t, okay, plus 1 times sine t. Okay, dt. Okay, let me clean this thing up. I'm actually going to factor some things. If I distribute the 15 here and the sine t, okay, and what I get is I get 30 times t minus sine t times 1 minus cosine t plus, this is going to be 30 sine t times 1 minus cosine t plus 15 sine t dt. Okay, all integrated from 0 to 2 pi. Okay, and so what I'm going to do is I'm going to factor out the 31 minus cosine t. So I get 30 times 1 minus cosine t. Okay, times t minus sine t plus sine t, and then I have this other term out here, plus 15 sine t dt. Okay, and the sine t's are going to cancel, leaving me with 30t times 1 minus cosine t times, or that's it, plus 15 sine t dt. Okay, I'm going to distribute the 30t. Again, a lot of algebra before we even do the integration on this one. So 30t minus 30t cosine t plus 15 sine t dt. Okay, again, 0 to 2 pi. And I think we're about ready to integrate now. Okay, now I'm going to integrate this in pieces, okay, because I need to actually integrate the middle here by the middle. The middle here, I have to integrate that by parts, okay? So I'm gonna do this individually. So 30t, that's going to become 15t squared evaluated from 0 to 2 pi. Okay, minus, and then I'm going to integrate this thing, okay, minus the integral of 0 to 2 pi of 30t cosine t, right? Okay, plus, okay, 15 sine t, integrate that, that's minus 15 cosine t evaluated from 0 to 2 pi. Okay, well, there's a dt here. Okay, because I haven't integrated that. Okay, and so I'm going to kind of hold off on the evaluation of these for right now. I mean, I could plug that in on both sides, which is fine. Well, maybe I will do that. Maybe I'll plug it in for the. It's pretty simple, and it gets rid of some stuff too. So this is 15 times 2 pi squared. Well, 2 pi squared is 4 pi squared. 4 times 15 is 60 pi squared. So this is 60 pi squared. Okay, I plug in 0, I get 0. Minus, okay, this middle part, which I'll just put in brackets. Okay, and then this thing becomes the cosine. This is minus 15, right? Okay. Maybe I'll do a plus here. This is minus 15 because the cosine of 2 pi is 1. And so this is minus 15 times 1. And that's a minus 15 times 1 again. So what I end up doing is I end up subtracting and adding the same thing. And so this whole thing goes to 0. So that goes away, which is nice. And so I'm just left with 60 pi squared minus this thing in the middle. Now I'm going to use integration by parts on this. Okay, so I'm going to do a little pause here. Okay, and I'm going to say, well, my u is equal to 30t. My dv is equal to cosine t dt. Okay, so du is equal to 30 dt. Okay. And my v is equal to sine t. Okay. And so we want u, v to u. So this is going to be 60 pi squared minus 30 t sine t minus the integral of 30 sine t. Okay. This guy is evaluated from 0 to 2 pi, and this guy is going from 0 to 2 pi. Okay, dt. Okay. So 60 pi squared minus, okay, and then this sine of 2 pi is 0. And the sine of 0 is also 0, but if you plug in a 0 here anyway. So this thing goes to 0. A lot of nice things there going to 0 there. Okay, so this whole thing goes to 0 because if I plug in a 2 pi, that goes to 0. If I plug in a 0, it goes to 0. That's kind of nice. So I've got a minus. If I distribute the negative sign here, I've got a minus, so that's plus. Okay, the integral from 0 to 2 pi of 30 sine t dt. Okay, so now we've got 60 pi squared plus, okay, let's integrate this. This is going to be negative 30 cosine t, 0 to 2 pi, and we're kind of left with the same scenario that we had before, right up here, right? Where we have the negative cosine 2t, but what we end up doing is we end up adding and subtracting the exact same thing. And so that goes to 0, and so I'm really just left with that first term, which is 60 pi squared. That's it, okay? On number 2. Now, this is what I would like to call the hard way, because there's actually a much easier way. Now, I don't know if the book intended for you to do it the easy way. They pretty much intended you to do it the hard way. But there is an easier way, and that is if you use the fundamental theorem of line integrals, you can test this function f of x, y for to see if it's conservative or not. Okay, is this thing conservative? Well, what was our test for conservative? Well, it was, q dx, does that equal dp dy, right? dq dx, does that equal dp dy? If we look at our dp dy, right? Well, p has no y values. Okay, remember our function. Whoa, what the heck just happened there? Okay, remember our function was f equals 30xi plus 15 times 2y plus 1j, right? So if you take q here, okay, and p, if you take q and try to do a partial with respect to x, all you get is 0. Boom, 0. And if you take p with respect to y, okay, well, there's only x's there, and so you get 0, right? So is this conservative? Yes, it's conservative. Therefore, we can use the fundamental theorem of line integrals. Well, how does that work? Well, what we would do is we would say, okay, that this integral, this work integral, f dot dr, okay, is going to be equal to the parent function, little f, evaluated for r of b, minus little f, evaluated for r of a. Okay, and so we just need to find what that little f function is. So if f sub x, the partial of x, was equal to 30x, then what would be the, what would be the f of xy function here, the parent function? Well, let's integrate this with respect to x. Well, that's going to be 15x squared. Okay, what about f sub y? Well, f sub y, okay, that's going to be 30y plus 1. So 30y plus 15. Okay, when I distribute. So what's that going to become? This is going to become f of xy. Okay. And this f of xy would also have a g of y plus k. Okay, so just keep that in mind. Okay, and then this thing's going to be 15y squared, because we're going to be integrating with respect to y, plus 15y plus, I'll say some g of x plus k. Okay, and so I'm just going to sub these, in for the functions that we don't have. And so we know that the entire parent function was f sub xy, little f, was equal to, okay, 15x squared plus 15y squared plus 15y plus k. Okay, and then, well, what are we doing here when we have b and a? Well, those are my parameters for t, right? So what is a and what's b? Well, t, we said, went from 0 to 2 pi. Okay, and so the integral would be 0 to 2 pi, right? So a would be 0 and b would be 2 pi. So all I have to do is evaluate this thing, okay, at 0 and 2 pi, right? Okay, so, well, what is this thing evaluated at 0 and 0 and 2 pi? Right, so f of, what am I doing here? I need to find first, what x and y are in terms of r. So x is equal to, in terms of r, what was r of t? R of t was, I'll just write it here, because I do need to parameterize this. R of t was equal to t minus sine t, okay, I, plus 1 minus cosine t j. I just need to figure out what x and y are, and then I can plug in my values here. Okay, j. Okay, and so t, this would be x, and this would be y, right? Okay, so let's find out, well, what's r of 0? What's r evaluated at 0 for my a value? Okay, that's when t is 0. So this is equal to 0 minus sine of 0. Okay, I'll use vector form here, comma, and this is 1 minus cosine 0. 1 minus cosine 0. Okay, so that's r of 0. This is going to be 0 minus 0, which is 0. And then this is going to be 1 minus 1. 1 minus 1, because cosine 0 is 1. So that's 0. So that becomes vector 0, 0. So x is 0. Okay, so x is 0 when t is 0, and y is 0 when t is 0. Okay, what about r of 2 pi? Okay, this is going to be 2 pi minus the sine of 2 pi, comma, 1 minus the cosine of 2 pi. Okay, so this becomes, okay, 2 pi minus the sine of 2 pi, that goes to 0. And then 1 minus cosine 2 pi, that goes to 1. So we're just left with 2 pi, comma, 0. Okay. So now we can evaluate. We can go up here and evaluate our function. Okay. Right? F of r of 2 pi minus f of r of 0 is equal to, okay, 2 pi is the vector, okay, x is 2 pi, y is 0. So this is plugging it into my parent function here, okay, is 15 times 2 pi squared plus, okay, 15 times 0 squared plus 15 times 0, right? The y's are always 0 in this case, okay, plus k, okay, minus, what's r of 0? Well, those are all zeros, right? So r sub 0 is 0, 0. So this is just 15 times 0 squared plus 15 times 0 squared plus 15 times 0 plus k. Okay, the k's are going to subtract out. This is 0, 0, 0, 0, 0. The only term that survives here is 15 times 2 pi squared, which is 60 pi squared. So again, you could use the fundamental theorem of line integrals just as easily. It's a few less steps than doing all that integration, and it saves you from doing integration by parts, which can be a pain, right? Okay. So a pretty long problem, but I did want to show you how to do it both ways, so that so yeah. Okay, let's move on to number 3. Okay, so number 3 says, determine whether or not f is conservative. If it is, find f such that, yeah, we just found a parent function, so we want to find the parent function. Okay, or it's really called the potential function, but I like to call it the parent function. I don't know. Okay, it's all good. Okay, so yeah, let me write this down. Okay, for number 3, f is equal to the function here is 4x times cosine y minus y cosine x, 4x cosine y minus y cosine x, okay, I plus negative 2x squared sine y minus sine x, sine y minus sine x, j. Okay, so we want to know, is this thing conservative, right? Is this thing conservative? Well, how are we going to find out if it's conservative? Well, again, we want to do, does dq dx equal dp dy, right? Okay, does dq dx equal dp dy? We're going to put a question mark there because we don't know yet. Okay, so we're going to take this guy and do the partial with respect to x. Okay, so partial with respect to x there, that's going to become negative 4x sine y, because the sine y is just a constant. Okay, minus the sine of x is cosine of x, minus cosine of x. Okay, so that's this guy, dq dx. Okay, let's try dp dy. Okay, let's take this guy. This guy, derivative of cosine is negative sine, so that's negative 4x sine y minus, okay, the derivative of y cosine x is just cosine x. Okay, oh, look at that. And what do we know? We know that it is conservative, that it checks. So this is conservative. And so they're asking us just to find the parent function. They're not asking us to find a line integral using the fundamental theorem of integrals, or sorry, the fundamental theorem of line integrals. Okay, and so we're just finding the parent function. So we want to now, excuse me, we want to integrate these each. So I'm just going to go f sub x is equal to 4x cosine y minus y cosine x. So I would want to integrate with respect to x here to get my I component of my parent function. So let's go ahead and do that. Integrate with respect to x, that's going to be 2x squared cosine y. Okay, integrate cosine, that goes back to sine, so minus y sine x. Okay, plus some sort of function in terms of, again, I'll just put function in terms of y plus k, right? Because we don't know if there was just a function in terms of y that got partial derivative, derivative did, that's not even a word. Partial differentiated, oh, there's the word. Okay, got partial differentiated out, right? And just became 0. Okay, so we'll put that g of y there. Okay, so f sub y, what's that going to be? That's going to be my second term here, the j term, and we're going to integrate that guy, right? So this is negative, this is, sorry, it's not negative. What are we doing here? No, it is. Was it a negative or positive? It was a negative. Yeah. So negative 2x squared sine y, right, minus sine x. Okay, so let's integrate this guy with respect to y. So the negative 2x squared, that's a constant. The negative, oh, that's why it becomes a positive, because when we integrate sine, we go back to negative cosine. So that becomes 2x squared cosine y minus, this is going to be y sine x, right? Because the sine x is just a constant. So we integrate that with respect to y, and we get the extra y there. Plus, I'm just going to put a g of x plus k. And notice something interesting. There is no g of y, and there is no g of x because I get the exact same thing, which is really kind of cool. Okay, and so what does my parent function end up being? It just ends up being 2x squared cosine y minus y sine x, getting ahead of myself, sine x plus k. There's no extra terms that I have to worry about. And that is my parent function, or what they call potential function. Okay. Okay, so that's number 3. Okay, number 4 here. Okay, number 4 says, find a function f such that the f is, oh, and now we want to, okay, so here we do want to find the potential function and use it to evaluate. Well, we're going to use find the potential function, or the parent function, to do a fundamental theorem of line integrals. Okay, so again, I don't want to have to parameterize this and do this all by hand. That would be a pain. Okay, especially with all those square roots and stuff there. That's not going to be fun. Okay, and the cube roots, or the cubes of the square roots. Okay, so let's use the fundamental theorem of line integrals for number 4. Okay. Okay, so we want to find, we have f is equal to, okay, the gradient of f such that, let's go back here, f is equal to the gradient of s such that f is equal to x cubed y to the 4th. Okay, so f, capital F, is equal to x cubed y to the 4th I plus y cubed y x to the 4th, y cubed x to the 4th, y cubed x to the 4th j. Okay, and r of t is equal to, this is the complicated one, okay, radical t I plus, so radical ti plus 1 plus t cubed j. Is that right? I think that's right. T cubed j. Yeah, that's right. Okay, so again, let's take f sub x of the parent function. That's going to equal x cubed y to the 4th. Okay, I plus, or no, this is not I. That's just that. Okay, and f sub y is equal to y cubed x to the 4th. So I'm going to integrate the first one with respect to x, and I'm going to get 1/4 x to the 4th y to the 4th. Integrate the second one with respect to y, and I'm going to get 1/4 x to the 4th y to the 4th. Okay, that's kind of cool. Okay, so it's kind of like I got a match there. So f of xy, the parent function, is equal to 1/4 x to the 4th y to the 4th plus k. So there's my parent function. Okay. So now how are we going to evaluate the integral? Well, let's see what the problem's asking us again. It says we want to go and let's plug in our, let's see what our r of t is. Okay, we want to eventually evaluate this integral, this line integral. So r of t, again, is equal to this thing up top, right? So I'm not going to rewrite it again. But what does t go from? T goes from 0. That's what I need. I need my limits of what t is. T goes from 0 to 1, right? So I'd really like to find out, well, what's r of 1 equal to? So let's plug in a 1 for t. That's going to be 1I, or just I. Okay, plus, okay, the square root of 1, I, which is just I, plus 1 plus 1 cubed, that's 2j. Okay, plus 2j, right? Okay. Okay, and so if I kind of put this in component form, this would be 1 comma 2, right? Okay, what about, okay, what about r of 0. Let's plug in 0 now. 0 evaluate, well, square root of 0 is 0, so that's going to be 0 I, okay, plus, and then this is 1 plus 0, which is 1, so that's just j, right? 0 I plus j, which is just 0, 1, right? 0, 1 there. Okay, so what we want is we want f of r of 1 minus f of r of 0, right? F of r of 1 minus f of r of 0. Okay, so, well, for r of 1, x equals 1, y equals 2, right? And so what was our parent function? Our parent function was this 1/4. Okay, 1/4, x is 1, so that's 1 to the 4th, times y is 2, so that's 2 to the 4th, minus, let's plug in 0, 1 now. This becomes 1 to the, or 1/4, and then this is 0 to the 4th. So no matter what else I plug in, it's just the whole thing's going to go to 0. So that one goes to 0. Okay, and so this becomes 16 divided by 4, which is 4. And so the answer there is 4. Okay. Okay, number 5. Okay, let's go see what number 5 is. Evaluate the line integral over the curve C. Okay, evaluate the line integral over the given curve C. Okay, so this is a line integral, and look at that, it says ds. That's my little s there. That means I'm going to have to use the square roots. Okay, I'm going to have to find the arc length. Okay, I'm going to have to use that arc length portion of it. Okay, ds. Okay, and with the line segment joining this, so I'm going to have to actually parametrize that line segment using vectors. So just keep that in mind. Okay, so we want the integral over c of 3xy ds. Okay, so I want to parametrize the line segment. That's little s, by the way. Okay, you'll know it's a big S if you have a big S here and you've got a double integral. So again, this is not the same thing as this. Okay, that's a surface integral. This is a line integral. So this is a line integral. This is a surface integral. Okay, so keep that in mind. Those are completely different. Okay, so we're dealing with the line integral. Okay, so we want to know, well, what's r of t going to be in this case? Well, the formula for a line segment, okay, is 1 minus t r naught plus t r sub 1. Okay, and so what is r naught in our case? R naught is a -5, -7. Okay, -5, -7. I just made the first point a vector. Okay, and r1, okay, is equal to 3, 1, I believe. Is that right? Yes. Okay, and so we're going to say r of t, okay, when t goes from 0 to 1, okay, so this is 0 is less than, t is less than 1, 0 to 1 here. Okay, okay, so we're going to go plug in 1 minus t, r naught is -5, -7, plus t times 3, 1. Okay, distribute this. I get -5 plus 5t, and then negative 7 plus 7t, plus 3t t. Okay, so I'm going to add those vectors together. I get 8t minus 5 and t minus 8t minus 7. Okay, so that's r of t. Okay. And so now we want to know, well, what's the work done, right? So this is the line integral. Okay, what's t going to go from? Well, t is going to go from, I'll just write it like this first. F dot dr, right? F dot d. Sorry, it's not F dot dr. It's 3xy ds. 3xy ds, right? ds, okay. So we want to keep this in terms of x's and y's. So what is x here? X is equal to, okay, 8t minus 5. And what's y equal to? Y is equal to 8t minus 7. Okay, so what's this going to be? This is going to be 3xy, okay, or what I'm going to do here is I'm going to do this. I'm going to do, I'm going to do 3x of t, y of t. Okay, ds is the line integral, so that's the square root of 1. Okay. Nope, it's not 1. It's square root of dx dt squared plus dy dt squared. Okay. Yeah. Pretty sure that's correct. Let me just verify that real quick. Yes, that's correct. Okay. Yeah, that was the very first formula that we had. Okay. Because the formula that we're working with is this one. Okay, it comes to us from this formula here. C of f of xy ds is equal to the integral a to b of f of x of t comma y of t square root dx dt squared plus dy dt squared. Yeah, that's the very, very first formula that we went over in this chapter for 16.2, just making sure I got the formula correct. Good. Okay. Okay, so this comes from this formula here. Okay, stars on that. Okay, so what is x of t? Well, that's going to be the integral. T is going to go from 0 to 1. Okay, of, this is going to be 3, and this is going to be 8t minus 5 times 8t minus 7. Okay, and then the square root, what are these primes? Well, take x prime with respect to t, and I get 8. And y prime with respect to t, and I get 8. So this is 8 squared plus 8 squared. So that's 2 64s, or 2 8 squareds. So that just becomes 8 squared times 2. Take the square root of that. That just becomes 8 radical 2. I have this 3 on the outside. 3 times 8t minus 5 times 8t minus 7. So I'm going to pull out the 24 radical 2 out in the front. And I'm going to multiply out the 8t minus 5 times 8t plus 7. And this is all dt now. Okay, dt. And so this is going to be 64t squared. This is going to be minus, this is going to be 12 eighths minus 12 eighths, which is not 12 eighths. It's 12 times 8. It's 12 eighths. Okay, 12 times 8 is 96, so that's minus 96t, and that's plus 35 dt. Now it just becomes a simple integration. Okay, and let's go back to my notes. Okay, so this thing becomes 64 over 3t cubed minus 48 t squared, okay, plus 35t, evaluated from 0 to 1. So I just plug in the 1, and it just becomes 64 thirds minus 48 plus 35. And this is 24 radical 2. Okay, so for negative 48 and 35, that's 13. So 64 over 3 minus 13, 24 radical 2. So now it just becomes simplifying the numbers here. This is 39 over 3 minus 64 over 3. This is 24 radical 2. 64 minus 39, that's going to be 25 over 3 times 24 radical 2. And that's going to be cross cancel. We get 8 times 25, and that's 200 radical 2. That's it for number 5. Okay. Number 6. Okay. I'm going to take a 1 second break here and go get a drink because my mouth is a little parched. So just hold on for 1 second. Okay, everybody doing okay? Everybody still following along? Okay, nobody falling asleep yet? Wake up. Okay, we're halfway through. Okay, both in time and in problems. Okay. Okay, everybody doing okay?
Yes, everything okay.
Okay, sounds good. I got it. Thanks. Okay, so I need to go back to where are my controls? There they are. Okay, share screen. Share. Okay, let's go back to, sorry, I just need a little break. Been talking for the last hour straight. Okay, number 6. Okay. They tend to get a little bit easier from here on out. Okay. Okay, number 6. Okay, evaluate the line integral, another line integral. Woohoo, okay. So we're going to evaluate this line integral. Again, notice the ds, the little s, that means we're going to have to use the square root. Okay, and here we have x, y, and z this time. Okay, x, y, and z. Okay, so we have 6 times the line integral y, z, cosine x. Okay, ds. Okay, and x is t, y is cosine t, and z is sine t. So x is t, y is cosine t, and z is sine t. Okay. Okay, so That's kind of cool. And so I do need to find the derivatives of these. So what's x prime? Well, that's 1. What's y prime? That's going to be negative sine t. And what's z prime? That's going to be cosine t, right? Okay, so what's this going to be? 6. Okay, and what is t going to go from in this problem? I think they tell me. Yeah, they tell me t goes from 0 to pi, right? So I need to know that to set up my integral. So 6 from 0 to pi. Okay, we're going to parameterize this thing. Okay, so y of t is cosine t. Z of t is sine t. Okay. Wait, did I write that down right? Yeah, that's right. Okay, that's good. Yeah. Okay. Yeah, okay, perfect. Okay, and then cosine x. What's cosine of x? Well, that's another cosine t, right? And then we need our square root, okay, our square root function here. Okay, and so this is going to be x prime squared, that's 1 squared, plus y prime squared, that's negative sine t squared, plus cosine t squared. Okay, so this becomes 6 times 0 to pi of cosine squared t sine t times the square root of 1 plus this is just going to be sine squared plus cosine squared, which we know is our Pythagorean identity of just 1. So that just becomes 1 plus 1, that's square root of 2. So this is 6 radical 2 times the integral of 0 to pi of cosine squared t sine t dt. There's a dt over here. Okay. Okay, so what are we going to do here? Well, we're going to do a u sub, okay, on cosine. So u is equal to cosine t, du equals negative sine t dt, okay. So this is going to become negative u, right? Negative u squared. Okay, evaluated, I could do my u of pi. What's the cosine of pi? That's negative 1, right? And then what's the u of 0? Well, that's just 1. So this is 1 to negative 1. So it's just kind of weird, but it's all good. Okay, I could reverse my limits of integration by multiplying through by a negative, which is 6 radical 2 negative 1 to 1 of u squared du. Okay, and so this just becomes 6 radical 2. This is u cubed, do the integration, and this is negative 1 to 1. So this is 1/3 minus negative 1/3 times 6 radical 2, which becomes 6 radical 2 times 2/3. Okay, cancel. And I'm just left with 4 radical 2. Okay, that's it for number 6. Okay, number 7. Oh, number 7 is kind of a cool problem. Okay. Last 4 problems here. Kind of moving into the home stretch because 8 and 9 are really easy problems. Okay, well, sort of easy. Some computation, but not too technical. Okay, use Green's theorem. Green's theorem. Ooh, okay. What was Green's theorem? Let's try to remember Green's theorem here. Okay, to find the work done, right? Okay, done by the force. Okay, of this guy, and then moving a particle along the x-axis from 0 to 1, or from the origin to 1, 0, and then 0 to 1, and then back to the origin. So basically, we're going to use Green's theorem to turn a line integral into an area, right, a double integral with an area. We're going to integrate over the area instead of doing three line integrals. We'd have to do 3 line integrals because we'd have to set it up as a triangle here. Okay, if we look at what we're talking about, okay, this guy here. Okay, so here's the triangle. We're going to go this way, and this way. And so I could do 3 line integrals, but that would be a pain when I could just use Green's theorem to integrate over the area. Okay, so I don't want to do 3 line integrals if I don't have to. That would not be fun. Okay, so f is equal to x times x plus 3y I plus 3xy squared j. Okay, so what does Green's theorem say again? Okay, let me pull out the exact definition for Green's theorem. Okay. Okay, the exact definition says that if we have a line integral over C such that P dx plus Q dy, that's going to be equal to, okay, you know, where it's positively oriented, right? That's what that little circle means here, is positively oriented. Is this positively oriented? Yes, it is. We're going from 0, 0 to 1, 0 to 0, 1, and then back. That's counterclockwise, which is positive orientation. So we're good. Okay, and that equals the double integral over my domain of dq dx minus dp dy, okay, dA. Okay, so that's Green's theorem there. Okay. Okay, so how are we going to use this to help us out here for this problem? Well, we want to integrate over the area, and we want to do dq dx minus dp dy. So what's going to be q in this case? Okay, or p. Let's start with p. P is going to be my first term here. Okay. Yeah. So p is going to be my first term. So I'm going to take x times x plus 3y. Okay, I'm going to distribute that, x squared plus 3xy. And I'm going to take the derivative with respect to y, right? And I want dp dy. Okay, so what's the derivative of this thing with respect to y? Well, that's just going to be 3x, right? Okay, so that's 3x. Okay, because the x squared is going to go away. Okay, what about q? Q is going to be that second term. That's going to be 3xy squared, and we want this one with respect to x, right? So dq dx is equal to, okay, 3y squared, right? Okay, so we want the double integral over d of dq dx. So what was dq dx? It was 3y squared minus dp dy, which is 3x dA over that area A there. Okay, so we need to find out what is that area. Well, the area is just a triangle, right? We need to change dA into dx dy's. So I want to integrate first with respect to y and then with respect to x. So I've got to know, well, what are my functions here? What are my limits of integration? Okay, so this is going to be dy dx. Okay, 3y squared minus 3x, dy dx. So the limits of integration, okay, are what's y going from? Y is going from 0 to negative x plus 1. This is the function y equals negative x plus 1. Y equals negative x plus 1. Why is that? Because we have a y-intercept at 1, right? A y-intercept at 1 and a slope of negative 1. Okay? Slope of negative 1 here. Down 1 over 1. So that's negative x plus 1. Okay? So this is going to go, the y is going to go from 0 to 1 minus x. And where the x is going to go from? Well, that's real easy. They just go from 0 to 1. The x's go from 0 to 1. And so now I'm going to integrate this thing with respect to y first. So this just becomes y cubed minus 3xy evaluated, okay, from 0 to 1 minus x. So plug in 1 minus x every time I see a y. I get 1 minus x cubed minus, okay, 3x times 1 minus x. Okay, and that's going to be integrated from 0 to 1 dx. Okay, 1 minus x cubed. I could do a u sub on that, or I could just multiply it out. I might just multiply it out just for kicks and giggles, just because I can combine that with some terms in the second one, the second product here. So 1 times 1 times 1, that's 1. Okay, 1 squared times negative x. 1 squared times negative x times 3. We're going to use Pascal's triangle here, right? Remember Pascal's triangle, 1, 3, 3, 1. Does that make sense? Pascal's triangle. So this is going to be 1 times 1 cubed, okay, plus 3 times 1 squared times negative x, plus 3 times 1 times negative x squared, plus negative x cubed, right? So that's using Pascal's triangle. And then minus 3x plus 3x squared. Okay, so let's try to clean this thing up. This is 1 minus 3x plus, or sorry, minus, nope, that's plus 3x squared, okay, minus x cubed, minus 3x plus 3x squared. So I'm going to combine the like terms here. So this is 1 minus 6x plus 6x squared minus x cubed. Okay. And now I need to integrate. Integrate 0 to 1 on x, right? Integrate this guy. So this 1 becomes x. This becomes negative 3x squared. This becomes 2x cubed. And this guy becomes minus 1/4 x to the 4th, right? Okay, and I'm going to evaluate that 0 to 1. So this becomes 1 minus 3 plus 2 minus 1/4. 1 minus 3 is negative 2, plus 2 is 0. That all goes to 0, and I'm just left with negative 1/4. Woohoo, using Green's theorem. Okay, let's do 8 and 9. Okay, well, let's start with 8. Okay, 8 says that I want to find the gradient, or sorry, find the curl of 8x cubed zi plus 0j plus 5xz to the 8th. Let's find the curl on that one. Okay, so, okay, f is equal to 8x to the 8th zi plus 0j plus 5xz to the 8th k. Okay. Okay, and so we're going to do our curl, which is our gradient crossed with our function. So I, j, k, okay, d dx, d dy, d dz, okay, and then our first term is 8x to the 8th z, 0, and 5xz to the 8th. Just checking to make sure I wrote that down right. Yes, yes, yes. Okay, so now let's find our determinant here. Okay, so what's our determinant going to be? And so let's do the ith component here. Well, this is d dy of 5x z to the 8th, which is 0. This has no y component, so that's just going to be 0. Okay, and then this is 0 times ddz of 0 minus dz of 0. Okay, so this whole thing goes to 0. Okay, so that's 0i. So that's kind of interesting. Okay, minus, let's do a minus there. Minus, what's j going to be? J is going to be ddx of 5xz to the 8th. Okay, minus ddz of 8x to the 8th z. Okay, j. Okay, and then plus k. Okay, what's k going to be? K is going to be ddx of 0, ddx of 0 minus ddy of 8x to the 8th z. Okay, so k, and again this goes to 0 and this also goes to 0, so we're really just left with that middle term j, right? Because there's nothing in terms of y here. Okay, and so when we take the derivative, it just goes to 0. Okay, so this is going to be minus the derivative with respect to x here, that's 5z to the 8th, minus, this is going to be with respect to z, that's just going to be 8x to the 8th. And it's j, the j component. Okay. And so I'm just going to distribute that negative sign, and it becomes 8x to the 8th minus 5z to the 8th j. That's it. That's the curl. It's the curl of f there. Okay, number 9. Okay, let's see. What does number 9 say? Find the divergence and the curl of the vector field f. Okay, divergence and curl. So here we want to find the divergence and the curl of this vector field. Okay, so let's write down the vector field first. Okay, so the vector field is f equals cosine z, cosine zi plus 3y sine z, 3y sine 3z j plus 6x cubed z k. Let me just make sure I wrote that down correctly. 3y cosine z, 3y sine z, 3 sine 3z plus 6x z x cubed z. Yes, looks good. Stop. There we go. X. Okay, perfect. Okay, so let's find the divergence first. The divergence of f is equal to the gradient dotted with f, right? So we want to take the first one, ddx, okay, ddx of cosine z plus ddy, that's a partial, okay, ddy of 3y sine 3z, okay, plus ddz of 6x cubed z. Okay, so ddx of cosine z, that's just 0. Okay, ddy of 3y sine 3z, that's just 3 sine 3z. Okay, And then this guy, ddz of 6x cubed z, that's just going to be 6x cubed. So I'm left with 3 sine 3z plus 6x cubed, and that's my divergence. Okay. Let's find the curl of this. Okay, the curl of f is equal to the gradient crossed with f. So once again, we're going to do ijk. Okay, and we're going to get ddx, ddy, ddz. Okay, this is cosine z, 3y sine 3z, and then 6x cubed z. Okay, so let's see what I is going to be here. I is going to be ddy of 6x cubed z, which is going to go to 0. Okay, minus ddz of 3y sine 3z. Okay, I. Okay, minus, what's j going to be? J is going to be ddx of 6x cubed z. Okay, minus ddz of cosine z. Okay, j plus, okay, so let's see what's k going to be. K is going to be ddx of 3y sine 3z minus ddy of cosine z. Okay. Okay, so ddy of 6x cubed z, that has no y values, so that just goes to 0. Okay, okay, dd minus ddz of this thing, well, the derivative of this thing is going to be 3y, it's going to be minus 3y times, let me move down a little bit, minus 3y times the sine of 3z, so that's going to be the derivative of 3z, which is cosine 3z, times the derivative of 3z, which is 3 times 3. Okay. Yep, that's I. Okay. Next one is going to be minus the derivative with respect to x here. That's going to be 18 x squared z. Okay. Plus minus negative sine z. Okay, j. And then plus, I'm not even put it in because when I take the derivative with respect to x of this thing, that goes to 0. And when I take the derivative with respect to y of this thing, it goes to 0 because there's no variables there that correlate. Okay, so I'm going to get negative 9y cosine 3z I. Okay. Okay. Minus, okay, 18 x squared z plus sine z j. That's the curl. Nice. Okay, number 10, we're on our last problem here. It's kind of cool. Okay. Okay, last problem. Okay, number 10. Use Stokes' theorem to evaluate this guy, okay, evaluate the line integral using Stokes' theorem. Okay, where curve is C is the curve of the intersection of the hyperbolic paraboloid, z equals y squared minus x squared, and the cylinder, x plus y equals 25. Oriented counterclockwise is viewed from above. So it's an intersection of these. Okay. And it's a line, it's a surface, and it's a line integral around that surface. Okay. Okay. So let's pull out some key information here. Okay, so f of x, y, z is equal to 6yx squared I plus 2x cubed j plus 6xyk. Okay. Okay, and then what are the surfaces that we're dealing with? That's the force field that we're dealing with. Okay, the vector field. Okay, what are the surfaces that this vector field is acting over? Well, we have the hyperbolic paraboloid z equals y squared minus x squared, and we have the cylinder x squared plus y squared equals 25. Well, let's make a diagram here. Okay. Okay, x, y, z. Okay, so the cylinder, that one's kind of easy. It's just going to have radius of 5. Okay, it's just going to have radius of 5, and it's a regular cylinder because the base is made out of a circle. Okay, radius 5, and this is going to go in both directions forever. Okay. Okay, and then the hyperbolic paraboloid. Well, if y and x are 0, then z is 0. So I would get 0, 0 there. Okay, so that's where it starts, and then z gets bigger as y gets larger. If y is bigger than x, then z grows. Okay. So if you let z be a constant there, you could see that that's a hyperbola, and so we get this kind of like hyperbolic paraboloid. Okay, and so this is a hyperbola. Okay. Hyperbolic shape that kind of looks like that. Okay. It's not a paraboloid, it's a hyperboloid. Okay. And that hyperboloid looks like that. That actually doesn't. It continues on, but it looks like that because of the cylinder that it's trapped inside. Does that make sense? Okay. So that's the cylinder that is trapped inside. Okay. So so the intersection of these two is really, okay, the positive orientation of this guy here. Okay. And so yeah. Okay, so you know, if we really wanted to draw it, we could find the intersection of these two as well. So I mean, we could solve for z, okay, setting these equal to each other, but this is the general idea. Okay, this is c, and then down here is going to be d. Okay, so just keep this all in mind. Okay, so c and d. Okay. Okay, so what are we finding? What are we trying to find here? We're trying to find the line integral, f dot dr, okay, using the surface integral. This is what Stokes' theorem is. Stokes's theorem. Okay, f dot dr equals the double integral of s curl of f dot ds. Okay, curl of f dot ds, and that's a big S, by the way. That's a capital S for surface integral. We're integrating over the surface integral. I'm sorry, we're integrating over the surface. Okay, it's a surface integral. So it's asking us to find the line integral. Again, we need to know which one. Yeah, it's asking us to find the line integral. So we're going to go from we want to use the surface integral to calculate the line integral. Okay. Okay. Yeah. Okay. Okay, so let's find the curl of f first. Okay, because we're going to need to use that. So the curl of f, ijk, okay, of d dx, d dy, d dy, d dz. Okay, and this is going to be 6yx squared, 2x cubed, and 6xy. Okay. Okay, so d dx of, nope, sorry, d dy of 6xy minus d dz of 2x cubed, I, minus d dx of 6xy, okay, minus d dz of 6yx squared. Okay, plus d dz, okay, sorry, plus d dx of 2x cubed minus d dy of 6yx squared. Okay, this is j and that's k. Okay, let's see what we got here. Okay, so d dy of this is going to be 6x minus 0 I minus, this is going to be 6y minus 0j. Okay, plus, this is going to be 6x squared, minus, this is also going to be 6x squared. d dy of this is 6x squared k. Okay, and so I'm just left with 6xi minus 6yj plus 0k. Okay, nice, nice, nice. Now, how are we going to do this guy, the curl of f dot ds? Okay, we found the curl of this guy, right? Which is kind of a nice function. Well, this guy is the curl of f. Okay, but we can we can equate that to P, Q, and R. Okay, P, Q, and R, right? Okay, so, okay. Let me just make sure I'm doing this correctly. Yeah. So by parameterizing, okay, parameterizing this, okay, we have this guy here, okay, because what we're doing is we're finding a surface integral, right, which is our flux, but we're letting the curl of f be our f, basically. To find the flux, okay, to find the flux, we said that f dot ds, the surface integral of f, okay, of f, which in this case is our curl of f, okay, that's what goes in there. That's our curl of f, is equal to, okay, so just keep this in mind, that the f is really the curl of f. That makes sense? Okay. Okay, is equal to, and if we can parameterize x equals x, y equals y, and z equals g of x of y, okay, if we can parameterize this, then we can let this thing equal over our domain negative p d g dx minus q dg dy plus r dA. That's what we're going to be using here. We're going to be saying that the flux is equal to this, okay? And what are we going to let z equal? Well, z is equal to our function, okay? We're going to say x is equal to x, y is equal to y, and z is equal to y squared minus x squared. That's what z is equal to, okay? Okay, that's going to be our hyperbolic paraboloid, that surface that we're integrating over. Okay, so again, this really is the curl of f, right? Because what we did was we changed the f into, right, the f dot dr into the curl of f, and we said, well, what was the curl of f? The curl of f was equal to this right here, okay, and so that becomes our f in our flux, if that makes sense. Instead of f, we're using the curl of f because that's what Stokes' theorem tells us to use, is the curl of f instead of f. It's still a vector field. It's just the curl. It's the normal to the original force field. Okay, but anyway. Okay, it's still, the curl is still a force field. It's just a different one. It's describing a different force field based on the original. Okay, so hopefully that makes sense. Okay, so we're going to take negative p dg dx. Well, we got what p is. What's p in this case? P is going to be 6x. Okay, so let's plug this in. So this is negative 6x. What's dg dx? Well, dg dx is going to be my partial of z, okay, right? Because that's my g of xy. Okay, g of xy is equal to, so that's a partial with respect to x. That's negative 2x. So that's going to be negative 2x. Okay. Okay. Okay, and then minus q. Well, what was q in this case? Q was negative 6y. Okay, And then what's dg dy? Well, dg dy is equal to this thing with respect to y, which is 2y. So that just goes in 2y. Okay, and then what's r? R is 0. Okay, dA. Okay, that's kind of getting bunched together, but you get the idea. Okay, so now I'm just going to multiply this together. So this becomes 12x squared plus 12y squared dA. Well, that's kind of nice. Why is that nice? Because our d, what's our d? What's our projection? What's our projection in the xy plane? Well, it's our circle of radius 5. And circles, I'm going to change to polar coordinates, right? I'm going to integrate over this area, but I'm integrating the double integrating over a circular area, so I'm going to want to change it into polar coordinates. Well, this is really nice because this x squared plus y squared becomes r squared. Wasn't that sweet? And if I change this to polar coordinates, I'm going to get an extra r dr d theta. And what's r going from? R is going from 0 to 5, and what's theta going from? 0 to 2 pi. And so this really just becomes 12 times 0 to 2 pi of 0 to 5 r cubed dr d theta. Okay, and I really like this problem. I'll tell you why in a second. Okay, and so this is going to be r to the 4th over 4, right? From 0 to 5. Okay. Okay, and so plug that in. I get 625 over 4. Okay, times the 12, so I could actually cancel that out, but whatever, we'll leave it. 12, 0 to 2 pi, right? D theta. So this is going to be the 12, I'm going to cancel. The 12 and the 4, that's going to be 3. And so I get 3. Okay, integrate this guy here. Okay, that's going to be 625 theta. 625 theta from 0 to 2 pi. We'll just multiply this times 2. Okay, whoops. Plug the 2 pi in for theta, and I get 6 pi times 625, which is 37. I'm not writing too well at the end here. 3750 pi. And that is the surface integral, or sorry, that's the line integral of the intersection of those two surfaces. So the intersection of two surfaces. Now, what I really like about this problem is that it had basically everything that we've covered in the course so far, basically in one problem. I mean, it deals with the curl, it deals with the flux, it deals with polar coordinates, it deals with surfaces in 3 dimensions, it deals with the domain of the functions, it deals with the intersection and the line integral of the functions, and it deals with the surface integrals of the functions. All of that jam-packed into one problem. That's kind of cool to me. And that's a great place to stop for the semester. That's it. So usually I add in a day or two in case I get ill or one of my children get ill. That didn't happen. The entire country got ill this semester. So since the entire country got ill and I was forced at home, we're done. This is it. So there will be no class on Thursday. Okay, we have 2 exams coming up. We have next Tuesday an exam. I will be in class next Tuesday. Your exam will be posted at 8 o'clock in the morning and you'll have until 11. Okay, and that will be posted in WebAssign. Okay, I'll be in class. It'll run exactly the same way. Okay, make sure that you're working out all your problems. In case I ask for one to be submitted at the end of the test, you have you have them all worked out. Okay. For the final, I will post the final 24 hours early before it's due, and you'll have 24 hours to work all of those out. Every single problem on the final must be worked out. It must be uploaded as a PDF. Okay, shared with me. I prefer you share it through me, through email at this point, but shared with me through email, and it must be in sequential order. Okay, so if you want, you could, for the final, you could print it off if you have a printer, or you could use OneNote or any other, um, uh, you know, you could, it will look like a regular exam. There will be space for you to write all your work in between the problems. Okay, so you could print it off and write out every single line. Now, if there are steps missing in your logic, you will get that problem wrong. Let me repeat that again. Treat this as if it were each problem were a mathematical proof. You are mathematically proving one line to the next. If you skip steps, you will get marked off. Okay, if there are jumps in your logic, even if you get the answer correct and there are jumps in your logic, you will get marked off significantly. So just keep that in mind. Okay. Okay, any questions about anything? Again, there's no class on Thursday. Okay. I will be posting this